Hello, everyone. Welcome to today's session. I want to talk about an important aspect of species distribution modeling, and this is about selection of background points. Well, in species distribution modeling, we normally have our study area, which can be a country, can be a range of a species, can be a continent or the whole globe, or just a smaller area. Now, within that small area, we normally have presence only data. Like we have only information about locations where a given species has been observed. We have no idea about the rest of the space. We don't know whether the species is absent in these locations or the species is there, but the sampling effort has not made it possible to record them from those locations. We can't say that these are absent locations because we don't know the level of detail under which the occurrence records or the presence points were obtained. If it were an intensive survey done within a small location, then we may confidently say these are absent locations, especially if they are within the dispersal capacity of the species. Like the species has been able to move to those locations, but still cannot establish a population or a sustainable population. So we may consider them absent. Otherwise, we may not say they are absent locations because maybe sampling effort has not reached there, or somebody went there, made observation, but recorded wrong data, or there was misidentification of the species, or they went in the morning and the species only appears in the evening. So we never know what happens. So how then do we pick background points? Because for most species distribution models or methods we use, we need to provide the model with presence locations as well as absence locations or environmental variables extracted from absent locations and present locations. Yet we only have presence only values. So different methods have been put forward to try to account for these, and even the methods used for analysis have been tailored. Some of them have been tailored to presence only data. Some work well with presence absence data, and some with presence and pseudo absence or presence and background points. Presence absence data, as I've said, only works when you intensively survey a location within which the dispersal capacity of a species is possible and made observations of the species at specific locations beyond which you didn't make observations or the species was not there. So you can say confidently that those are absent locations, a very rare phenomenon in ecology. On the other hand, we normally go with presence locations and then randomly pick background points within the study extent, assuming that those are locations within which the species has ability to disperse and establish population, but they have not reached there, or they have been there, but they have not established a population. So those are considered background. Now, in SDM package, there are 4 methods that have been implemented and one can use to build, to generate background points. One is randomly over geographic space. So within that study region or region of interest, you randomly pick background points. The other one, okay, this method has been used for a long time, for sure. The other one is the randomly picking background points from environmental space. So that is called e-random method in SDM. Now in that case, the method picks randomly within the environmental space, like picks random points or random environmental variable values at random pixel points, not necessarily geographic space. So it picks random points from the environmental variables you use as predictor variables. Thirdly, we have GDist, which is random within the geographic space, but there is weighting for distance, in the sense that regions that are very far from the locations of the presence points are given more weight or are more likely to be picked as background points. Lastly, we have the edist, which is now taking environmental values that are quite dissimilar from the environmental variables at the presence locations. Now let's see how this is implemented. First of all, we will use the library called SDM. You can see that when I load SDM, it requires Terra, and my Terra is up to date, version 1.8.42, and my SDM package is version 1.256. Then we can load existing presence-only data. We'll call it PO, for instance. And then we say, because it's data which comes with the package, we get it using system.file function. And then we provide external path. And then we say it comes from package called SDM. Now, if I just run this alone, it will take us to that folder. So we need to provide the file name itself. So it's called PO spatial points. .shp. So if you look at PO, it's providing us with the full path to where the data is, or the file is. So what we can now do, because already loading SDM loaded Terra, we just say vect this, like read that file using a vect function from Terra package. So now our PO is a spat vector object with 79 records and 3 variables, which is SP4, code X1, code X2. Now, this is presence only data. If you look at these values, they're just 111 of the SP4. That's the random name given to the species column, 11111. All the 79 has 111. And this is normally what we get when we download data, species occurrence data from, say, GBIF. For example, if I check geodata and then I look for SP occurrence of whichever species, maybe we talk of which one, Gravia, maybe Ziziphus mauritiana. No, that's quite a lot of records. I don't want to waste my time downloading all that. Which other species might have Cordia sinensis? How many records are there? Yeah, that's a bit less. Cordia sinensis is a wild edible plant. Yeah, so you can pick any species. I didn't download this because it had so many records and I don't want to waste time just checking, just confirming that most records are presence only records. So once it's downloaded, we can tabulate it, and we tabulate it based on occurrence status. Yeah, all 39 are considered present records. So if the occurrence status had some absent, then we will have a table of present and a table of present, absent and present. But here you can see everything is just present. So that's the typical presence only data. Predictor variables, which we can use with this, we can read them again using the system dot file function. And then inside this, we go for external folder. And then we provide the package name, which is still SDM. If we run this alone, it's just providing us with the path to the external folder. And if you decide, you might even be interested in checking the list of files inside there. So you can use list.files inside system.file, in which we have external and then the package is SDM. So all these are the files inside that folder. The ones that we want to use today is predictors.tif. So here we add the full path. So if we look at preds, it will be the full path to the file. Once we can reach the file, the next thing is to read it. So we add Rust function. And then in preds, now we have a spat Rust object. And this spat Rust object has two layers. One is bio15 and the other one is NDVI. So we have presence only data and we have predictor variables, the basic ingredients of building species distribution model. Now we can decide to visualize this. If you are wondering how that I popped up that, it is Control-Shift-R. Then we can plot the threads because we want to see whether they overlay, in which we provide maybe just one of the two layers. After plotting that, we are interested in plotting the presence only data, and then we can add it on top. So we add equals true. And we see here that we have the raster and then the presence locations, which are 79 in number, and we've just plotted one of the layers. Now, the main task of today was to generate background points. Control-Shift-R, then background. I want to create 4 backgrounds because I said we have 4 methods, grandom, erandom, gdist, edist. So I will have, that is Control Alt and down arrow. Then I just put B. Then I say background. function from SDM, and then our predictors are preds, and we provide n argument, which is the number of points we want. So for now, I want just to get points that are equal in number to the number of presence only records, which are 79. So I just use nrow PO, which is the same as to say 79. And then the method will vary. We will provide 3 different methods. If you want to confirm, I can run this alone like this, and we see 79. So this is just the same as saying 79. The first method I said is grandom. Grandom method will pick background points randomly within the extent of preds. And within the extent of preds, only where pixel values are valid, not NA, not the masked out areas. So only where we have true pixel values. Then the next one, we will do eRandom. And eRandom will now be picking points based on the values in the predictor variables. So it will not be looking at the geographic distance, but it will be just picking them based on the environmental variable values randomly. The third one is gdist. Now, because gdist is picking background points based on their distance from presence points, we need to add another argument, which is SP. And the SP is the species occurrence points, which is in the PO, presence only spat vector object. eDist is also taking environmental variables based on their distance from the environmental variables at the presence locations. So again, we add PO so that it knows it extracts the values from the preds using the PO and then ensuring that the distance for the background points are far from the values that are within the presence points. Now we will call this B1, B2, B3, and B4. The worst possible way of naming variables in R, because what if we get to B1 million? But I will just use it for now. So all those ran successfully, and you can confirm probably the head of B1 and see that there are values for B15 and NDVI predicted from random locations within the geographic space. So we have background points. Now, what I want to do, if you looked at the head of B1, we have X, Y, and the extracted values. This is the same pattern with B2. We also have X, Y, and the extracted values. But because these methods extract values differently, my main interest now is to see how different are these values. So Control Shift R again, I do visualization. I visualize them. Now for me to visualize them, these are all data frames. If you check the class of B1, B2, you will notice that they are all data frame, whether it's B5, B4, sorry, it's still data frame. So because they are data frames, we can bind them together to form one big data frame. But because they are the same. They have no column which will differentiate that this is from G random, this is from E random, this is from G dist, this is from E dist. We need to add that column. So again, I have my B1 to B4. Then I put $sign and I add a column. This is a way of creating columns in a data frame. And then each will get its own method. So let me say the first one will be grandom, the second one will be erandom, the third one will be gdist, and then lastly we have edist. The B here is B1, B2, B3, and B4. So when I do this, it means for each of these data frames, I'm adding a column, and that column is containing the value which corresponds to the method. So this will enable me to group them by this and do some comparisons. Once I've done that, I can now combine them, because now if I combine them, I will still be able to differentiate which ones are from this category, which one is from this group, and that. So to bind them, I can just use cbind, not cbind, but rbind. So another poor naming, bg all. But I can just use it for now. B1, B2, B3, and B4. So if we look at head of BG all, we can tell that these are from the G random group. The first 6 rows are from the G random. And if we look at the tail, which is the first, the bottom 6, they are from the edist method, these values. So these are pure data frame. There is no species distribution modeling here. We are now playing around with data frames. And this informs why sometimes it's important that you understand basic R before you start species distribution modeling. The way we add this column here, you can do it even using tidyverse, but I didn't want to load so many packages, so I just use base R approach. One of the base R approaches. Now BGAll now should have 79 by 4 rows. So if you check the number of rows of BGAll, it's 312, which is 79 times 4. Sorry. 79 times 4 is 316. But we expected the values to be equivalent, these values to be equal to this. Let me confirm again the number of rows of PO. 79. And I set n to be that. So let's see which one failed us. So we can check. I would have used lapply, but I've not made a list of all these. So B1 is fine. B2 is not fine. B3 is fine. B4 is also fine. So in B2, using the erandom, when the method tried to obtain pixel values from this region that are different from where the species has been observed, it could not get 79 pixels that are unique compared to the presence locations. So the maximum it could get was 75. I hope that is clear. Otherwise, it would pick points that are environmentally similar to the presence points, but that is what we are running away from. So we are not surprised that this is not a factor of 79 by 4. Then we can now also make our presence only records similar in terms of columns with the BG all. So if we check the head of PO, those are what we see. And when we check the head of BG all, that's what we see. So they are different. We need this PO also to have X, Y, X, Y, and we need to extract the values corresponding to these presence points, which is B15 and NDVI. And then we need to provide BG method, which of course will be the presence only. So we won't need grandom for it, so that we can combine it with this data to form a single big data frame, having presence and all the 4 different background types. We are interested in comparing them visually, which ones are different from the presence locations and which ones are a bit close. So with our BG PO, of course, it's a data frame. It's a sparse raster object, a sparse vector object. Sorry. We can use it to extract predictor variables, because currently it only has the occurrence records values X, Y, and the species. So we use it to extract the predictor variables. To do that, we can say P ovals, and P ovals will be, we will use the extract function from Terra, and then we provide preds, and then we say do that for PO. Now we have the extracted values corresponding to the presence locations. These are those values. However, the 79 of them. However, we don't have XY coordinates corresponding to this, but we need that to combine this data with the BG data. So we just add one argument called XY is true. XY is true will enable this to extract values and also corresponding X and Y axis values, Y coordinate values. So if we now check head of P ovals, we see that X and Y are now included apart from P15 and DVI. So what we need now to add is the column which contains presence, 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 presence. To do that is super simple, just as we did with the other one, P ovals. Then we add BG method. It must be the same as the other ones so that we can combine the two. Then we just put presence, because it is not background, it is the presence locations. So now our P ovals will be having all the columns that are in BG all. That is, it has the BG method, which is just presence, presence. It has XY, it has the extracted values. We don't need ID because we don't have it in the BG all. So what we do is to say P ovals gets P ovals, but pick all rows and only columns 2. What are the number of columns there? We can say ncol of P ovals 6, so up to 6, because we know the first one is ID and we don't want it. So you can also say -1 or 2 to 6. So our P ovals is now just the predictor variables, X, Y, and BG method, which is just the presence locations. Now we can combine it with the BG all. So to combine it with BG all, we can just say presence only and BG data will contain a bound version of PO vals, and we bind it with BG all. Yeah, so this is containing the values from this, presence only values and background values together. The next thing, if you wish, you can check the head of that POBG, which will start with the presence positions. And then if you look at the bottom, you will see the edist values. If you are still doubting something, then you can table it. You are free. You can table POBG. Then you table by BG method. So you see we have the edist, erandom, gdist, this one, and presence. Remember the erandom had that problem. Now, once we have this, we now need to plot to visualize. I just wanted to do this by plotting. I don't want to do an over test to compare the mean differences, although that's something one would think of. To plot it in R, largely we use ggplot. So that's why I'm loading the library ggplot. And then I say POBG. We push it to a function called ggplot. And then we provide aesthetics. This is again a reason why to do species distribution modeling in R, you need basic understanding of R. So in this POBG, we have two predictor variables, so we can just pick one of them, like NDVI. Then in ggplot, we don't use pipe again. We now use plus sign or symbol or operator. And then I just want to put a geom box plot. In this box plot, you can provide outlier color, outlier dot color. I think it's, yeah, it's that. Then we provide it with a color which is blue. Then we provide line width. That is how thick the lines around it will be. And then for the aesthetic side, we can also make the color a bit fancy. There is this function after scale, which we use to put in the color. If we run this, we should have the plots, which compares the NDVI values. Then we may not, we are able to see the presence values as a mean of around 100, a median of around 100 or something, slightly above 100. But then edist is very far away. The predictor variable values, the NDVI values from the background points are not the same. So the method you choose will expose different values of from background to the model to compare with the presence locations. So you can already assume, imagine that when you use these edist with presence data points, your model may be having very, very high AUC values just because these are so different from this, and the model finds it easy to separate the absence from presence. Then if you use grandom, they are the medians are a bit close. I have not used any p-value test or whatever significant level test to see whether they're significantly different or similar or whatever, but visually, just visually, please. So this might have quite low AUC or TSS or evaluation metric, or the model might appear less good, if you may say so. Just to maybe add some aesthetics on this to probably see that this is the presence, and we can change the scale fill, which we can just use manual because we want to manually set the color for presence. So for that, we can use the values argument. Then we provide a vector of the column name, which we can call presence. So if it sees presence, it gives it a color. Which one contrasts there? Maybe green. And then any other thing which you can put with other, we leave them as maybe white. Other than that, we can also say add this guide is none argument. So if we run that, presence scale fill manual, presence is green, other is white, then guide is none. I expected this to. Did I miss? Values gets, say, presence gets green, and then other colors get white, and then guide is none. Oh, I think I ran. What did I miss there? ggplot. Okay. I got it. So I did not specify that in the aesthetic here. I did not provide the fill. So, I mean, that's also the beauty of live coding. We miss some things. So we need to provide the condition that if bg method is exactly equal to presence, if that is exactly equal to presence, then we call it presence. And because it's a condition, the rest is other. Yeah, I think that should now fix the problem. Yeah. So now we have our, maybe I expand this if else thing for the fill, so that you can see it clearly. Just the condition to tell the program that if it finds the BG to be presence, then it should be considered presence, and that presence will be filled with a value of green. Other than that, still not so much satisfied with the look. We can alter the theme a bit. These are just aesthetics, so axis, nothing the values, it doesn't change any values inside here. It's just improving the look a bit. We can change the element text by specifying, for example, because the colors here look a bit gray, I want them to be quite black for the better contrast. So black is the color I choose, and then I make them a bit bold for more clarity. That is given by argument face, and then increase their size a bit to say 12. Other than that, other than the axis text, we can also change or improve the axis title, this BG method and NDVI. So we call it axis title, again, element text. What we do with the element text here is again make the color black. As you can see, I think the color is already black. No harm. And then something also to change here is to make it bold. Basically similar to what we had before. This bold should be in quotation marks. And then we make the size to be bigger than that of the labels. These have nothing to do with species distribution modeling, but just basic R knowledge in terms of visualization of plots. Element text, general text, we make everything to have the color of black on this our plot. Yeah, so you can see that the labels are now more visible compared to what we had before. If you go back, you see some light gray. What else? It still doesn't have a title, so we can add the title just using plus operator. That falls under labs function, and then for the labs we can change the x-axis label and maybe call it background method, because that is how Babak refers to them in SDM. Then for the y-axis, which is NDVI, yeah, you can just return it as NDVI by method. Of course, presence only is not the method. Where we have just the presence, it's not a method, but it's can just call it NDVI by method. The last thing is to give the table the plot title. And the title, we can just say NDVI by background method. That should put a title. The title is thin. The title is smaller than the labels on the axis, so that's an issue we can fix using them. The things you can do here are endless, so you can play around with it. Element text, because we are referring to the text. First of all, color black, that's probably the default. And then we make it bold. And we set the size to be the largest of everything. And horizontally, we adjust it by a value of 0.5 so that it's centered. Yeah. So I think that's sufficient for the plot. What now remains is for us to basically confirm that if we build a model with eDist and we compare that with the model we build using grandom, we get different evaluation metrics. It is like somebody comparing a leopard and a cheetah and somebody comparing a leopard and a tiger. Very, very far-fetched analogy, just to make it maybe clearer to somebody. So this is like eDist and presence points are like leopard and tiger, quite different animals. And I don't know the difference genetically or morphology or whatever, but just giving it from the point of view that you see two animals in front of you. You don't do any DNA or whatever complexities that the world has brought forward. I am a strong believer in simple things. Nothing complicated so far. Even what we are coding here are super simple. So to compare the models, again, Control Shift R, compare the methods, or even models. Those will be models now, not methods. So we will build a D object using edist, the background we obtain from edist. So you remember we do this using SDM data function, and then we provide the species column from the training set, which is presence only, spat vector object. Then the predictors, we provide preds, which is common to everything. But for the background, we provide B4. For edist, which we want to compare with this, I think that was the B4. Edist. Yeah. To build this model, okay, we want to compare it with the grandom because grandom is quite close to this, and we expect the performance or the evaluation metrics to be a bit low. So I can just duplicate this and then change this to grandom, and then SP4 as a function of everything. Train is PO, predictors is that, but BG is now B1. B1 is the background points we obtained using grandom. So this builds, those two lines of code builds the D or SDM data object, not the model. To build the model, again, we will need, let's call it edist. We will need SDM function, which is from the SDM package, of course. We again do SP4 as a function of everything. And then we provide the data object, which is from dedist. And then we provide methods. For now, I want to blindly use random forest. Remember, this may not be the best method to use with presence only data, but we will use it for now. I would have used Maxent, but I know sometimes Maxent is not easily installed and used by new users. Sometimes you might need to separately install SDK, JDK or Java Development Toolkit before you can run Maxent. So, but Random Forest is basically easy to install. We will test this using 30% of our data, and then we just run it 3 times. So I will drop down most of this so that you see which parameter is fed to which argument. After that, we duplicate the same. Don't repeat yourself, but I didn't create a list to loop through. So allow me to just repeat myself for this. Model for grandom, what we change here is only here. The source of data is now from D grandom. So if I build these two models, what was I saying? I was saying that random forest may not be the best method with the presence only data, but I'm using it because of the complexity in installing Maxent for some people. For me, Maxent will work here, no problem. Okay, first of all, let us check the AUC and then I will try the Maxent. Clear that. So edist, Sorry. For the eDist, where the backgrounds are quite different from the from the predictor values corresponding to presence locations, we attained AUC of 97 or 0.97 and true scale statistic of 0.87. In fact, because this is presence only data, TSS makes more sense than AUC. Probably those are beyond the need for today. Then for the MG random, if we look at MG random, our AUC is basically 0.88 and TSS is 0.67. So compare those two values. The other one was 9787. Now it's 8867. Quite low. And that is supported by what we see here. These values are so different from these, and therefore the model easily differentiates between locations that are suitable for the species from locations that are not suitable. But when they are quite close together, the model takes much effort. And the performance metrics may look a bit lower. I said I can run Maxent in my case. If you can run Maxent, you are free to do so, because probably I had installed the Java development toolkit. I have this small package installed, RJava or things like those installed. So I have no problem with that. medist. Maxent medist performed. Okay, evaluation metric here is lower than random forest. You remember it was 9787, I think. And then MG random is even worse. Of course, we expected it to be worse than edist in that case. So the evaluation metrics differ. Now, what is my conclusion to this? My message to you as you pick background points to run your model is to understand the region of interest. If your region of interest consists of areas that are environmentally very different from the locations where the species has been observed, then you might avoid using edist, because edist gives more weight to areas that are very different from the locations where the species has been observed. I hope you get that clear. And you should use the range, the known range of a species occurrence locations to define your region of interest. Sometimes the known ranges are not well defined, but try with a probably expert knowledge and all that to know the region of interest. Just using a country boundary or a continent boundary or something like that with edist, edist probably will be concentrating in picking points at the top of a mountain, while the species, which the species might not even be able to access. So those will be very different from the locations where the species has been observed, and therefore your model will be performing super nice, having very, very high AUC value and TSS values and all that. But then it may not be able to well differentiate areas where the species is able to disperse, but still not suitable for it. So the choice of any of these is important. Which one you use will affect your result and the trustworthiness of your results and even the prediction output. Another thing which I did not mention is that in the background function, there is an argument called bias. This one. Now, bias might be useful sometimes. Bias file can be useful in most cases, of course. If you know that the presence observations have been probably concentrated along road or along a river, or there is a variable which guided the presence location selection or survey. So you can use that limitation variable as a bias file in your background selection. So what that will help with is that the picking of background will now be more concentrated around the regions with more weight in the bias file, so that the background points will not just be picked very far away from the presence locations, but they will be relatively close to the presence locations. Not as close as G-random, but the limiting factor will probably be also influencing how far the species observations were made, or the sampling intensity. Other than this, you are free to pick background points from wherever you want within the geographic space, provided you can justify why you are doing so. There are not only 4 methods on Earth to do that. You can have a user-defined region of interest and then pick background points the way you prefer. And probably that's the beauty of all this, that you are not confined to any of this. Again, when you're doing species distribution modeling in another package, it does not necessarily have to be SDM package, but if you need to educatively or with some informed decision-making process, pick your background points, you are free to visit SDM package, use a background function, provide your predictor variables, provide the number of points you want, and then give it a method. It will just return for you a data frame with the background locations and the values. Then you can take that to whichever model you are using to build your species distribution model, whether it's Wallace, whether it's ENM-eval, whichever. There are so many packages for building species distribution modeling. But here, picking of background points has been simplified for the community. Well, maybe not to make it too long, thank you so much for listening. I will upload this code in my GitHub repository, and you are free to visit that repository and pick the code, play around with it the way you want. No need for attributing me in this, because this is just largely what we have in the package already documented in the documentation of the package. So once you use SDM, just attribute the creators of the package, but don't cite anywhere that from YouTube video or from GitHub repository of who, but just cite Babak. Sorry, I need to put this in quotes. Yeah, attribution should be given accordingly for the authors of the package. Thank you so much, and happy coding. We'll be happy to know your opinion on all this, whether this makes ecological sense to you, or this is useless and we need to move one step further and think differently. That's the beauty of science. This is not cast on stone. Maybe in the next century or the next 10, 20 years, people will be wondering how on earth were you blindly using these kinds of things to do analysis. These are not so important. Yeah, just like bioclimatic envelope or um, species distribution modeling that was just based on GIS framework where you compare locations with suitability and locations without suitability, building block or rectangular blocks around the presence locations to determine the potential suitable habitat of a species used to be the most nice thing to do. But now people will look at you like, are you seriously still using that? When we have neural networks, we have SDM, we have Wallace, we have ENM-eval, we have all these packages in R to make work easier. What I wanted to add here is that I'm using version that. For ggplot, most of the things will run. I don't need to say the version of ggplot. Thank you.